Okay, in this lesson, I'm going to talk about independent samples t-tests as well as dependent samples t-tests. And by way of introduction, all t-tests serve to compare two means. In the previous lesson, we talked about comparing the population mean to the sample mean, right? So that was a one sample t-test. Today, we're going to talk about independent samples t-test where we're comparing two separate groups. And we're going to talk about dependent samples t-tests where we have a group being measured at 2 points in time. We follow them. So we'll go into it. I have some of this stuff preset for the board, but we'll continue. So let me share my screen. All right, and I need to do the slideshow. All right, so as we have noted, in the past couple chapters, we've been trying to draw inferences about a mean of one population. Now, it's possible that you could be trying to draw conclusions about two separate samples or two separate populations. So when we talk about an independent samples t-test or independent groups t-test, we're going to compare two separate means from one another, and it might look slightly different, right? So, when we talk about standard error, we talked about standard error of the mean, and all data sets have some level of error. So this is a calculation on error. But if we have two samples or two populations that we're comparing, now we have to have a measure for standard error of the difference. Now, it's important to understand that the standard error of the difference is going to be the denominator for our independent samples t-test. And I'll go into it, but so let's take an example. Suppose we wanted to do a research study to determine whether caffeine improves performance on math exams. So you could test this hypothesis by randomly selecting two populations. So one population would be the experimental group. They would receive the caffeine. And then one population would be the control group, and they would just be there to serve as a comparison. Now, it's important to understand that most of the time we don't have probability sampling. We rely on convenience sampling. So we take volunteers and then we randomly assign them to either group. So standard error of the difference, as I noted, is we're really looking at the difference between two means, right? So we're specifically focused on what the error variance is for two different means. Now, in principle, the smaller the standard error is, the more confidence you have that the sample difference is reflective of the population difference, right? And the larger the error is, the less confident you're going to be, right? So here is part of your formula. This is not the entire formula, but in order to get a number that reflects variance, right, and also reflects error, we need to start with pooled variance. So you may recall from lecture 5, S squared referred to variance. If you have the subscript pooled, that means we're taking the variance for sample 1 and we're taking the variance for sample 2, and we're putting them together. When you pull something together, you're putting it together into a single estimate. So it's sort of like if you were trying to, I don't know, have a pizza party and you had 4 of your friends and you were going to pool your money together. Everybody would give what they had or what they could contribute, and then it becomes one pot of money. Same thing when we talk about pooled variance. We're taking the variance for sample 1 and the variance for sample 2, and we're reflecting it. Now, I want you to take a close look at this formula, pooled variance, you're going to have N1 minus 1. N1 means the sample size or the number of participants in group 1 minus 1. And then we multiply it against the variance for sample 1. Now, you'll see anytime you have numbers or letters next to one another, you multiply across. When I write it on the board, you're going to see I want to make it clear because it looks like a whole bunch of things are smushed together. So I actually put a parenthesis around the variance for 1, and then you add sample size, right? Number of cases for sample 2 minus 1 times its respective variance. So times the variance for sample 2 divided by the degrees of freedom, which is N1 plus N2 minus 2. And when we put it together, you will take the pooled variance and you're going to divide it by N1. And then you're going to take that pooled variance and then divide it by N2, and you're going to add it up and then take the square root. Now, this formula looks pretty busy. So there's a simplified formula on the right, which is standard error of the difference, is we take the pooled variance and multiply it by 1 over the number of participants in sample 1 plus 1 over the number of participants in sample 2. Together, if we were to smush it all together and combine it into one formula, this would be what our standard error of the difference formula looks like. All we did is take pooled variance formula and then the parenthetical statement of 1 over N1 plus 1 over N2. Now, I said that the standard error of the difference is the denominator of the formula. The numerator refers to the mean differences. So we're going to look for average 1 or mean 1 minus mean 2, right? So that's how it looks. Now, here is an example, and I've already preset it on the board, but I will have to set up my camera, is let's say a researcher was interested in whether people work better by themselves or whether they work in pairs. So she randomly assigned 16 participants to work either by themselves, right, working individually, or working with mixed gender pairs. And then they were given some kind of dependent variable. So the novel task was to, they were given a skill set or a task to learn, and then they measured how productive they were. So again, group 1, they worked alone. And in group 2, they worked in mixed gender pairs. So in order to do this, I'm going to stop my share. And I'm going to set up the board. And I'm going to set up the board in a way that I can explain some principles. So there are going to be numbers from the previous slide already preset. So give me a second to do that. Okay, so what we have here is I first put on the board, I don't know if you can see, the independent samples t-test. So we have x bar 1 minus x bar 2. So x bar 1, that refers to your first sample mean. X bar 2 refers to your group 2 sample mean. Now, if you go back to the numbers on your PowerPoint slide, you will remember that in group 1, the first mean, when they worked alone, the mean was 3.63. The second mean, when they worked in mixed pairs, the mean was 7.13. So all I did was put the numbers in for the numerator. Now, the denominator, as you may recall, was the standard error of the difference, which included, this is your pooled variance, and then we multiply it across 1 over N1 plus 1 over N2. So I said, okay, N1. How many participants were in group 1? 8 minus 1. Covered that parenthesis. Now, I said to you, let me close this parenthesis. I said to you that I like to put a parenthetical mark around the variance for a given group so that you know you're going to eventually multiply across. So variance for group 1. So now we have 8 minus 1 times 0.86 plus N2 minus 1 is 8 minus 1 times the variance for group 2, which is 0.71, divided by N1, which is there were 8 participants, plus N2, 8 participants, minus 2. So that's all there, times 1 over 8 plus 1 over 8. Okay, so now that I have everything there, I could start the process of calculating this mathematically. So the first thing I'm going to do is try and simplify what's going on here. So what the numerator was 3.63 minus 7.13. So the new numerator is going to be minus 3.5 divided by the square root of, and I'm sorry it got squished, but I'm going to need the whole space of the board. So what's 8 minus 1? We're going to do 7 times 0.86 plus 7 times 0.71 divided by 8 plus 8 is 16 minus 2 is 14 times 1/8 plus 1/8 is 2/8, which becomes simplified as 1/4. So now what you'll notice is that I already have simplified a lot of the numbers, but I'm not done my formula. So let me bring that up here, right? So we still have to work out our process. So minus 3.5 over what was 7 times 0.86. We get 6.02 plus, and again, I have to make sure the square root sign is there, right? Then we do 7 times 0.71, 4.97, divided by 14 times 0.25. Now, what's interesting, if you're wondering what's going on here, is that I'm slowly simplifying everything. So the last thing I'm going to do with the denominator is take the square root. So now we're going to do minus 3.5 over, now we have to do, well, okay, what is 6.02 plus 4.97? So that gives us 10.99 over 14. Again, don't forget the square root, times 0.25. So I'm just bringing it down and slowly working through the process. Okay, so now 10.99 divided by 14, what is that? So we have minus 3.5 divided by the square root of 0.785 times 0.25. Okay. So now the next thing we're going to do, before we can do the square root, we have to figure out, well, what is this value? So times 0.25. Here we have minus 3.5 divided by the square root of, let me just double check that, make sure it's right. It's 0.785, scratch that, 0.785, my calculator's not working, times 0.25, we get the square root of 0.196, right? So now we can actually, again, we're still carrying our work. I'm going to not bring it as high. So now we do the square root of 0.196, take the square root, and we get the following: minus 3.5 over 0.442. The next number is 7, so why don't we round that up to 443? Okay, so here we have, this is our actual t-value. So our final t-value is negative 3.5 divided by 0.443. And we get a calculation that looks like this. Our final t-value is 7.9006, which will make that 901. That is the final product of the independent samples t-test. Now, it's a lot of work, right? So we started with the formula. We had to start plugging in the numbers, and you'll notice we have to simplify this, right, to get to whatever numbers we need. So we're working within the square root. And what that does is eventually we're going to get a number that we can take the square root of. So we did all of this first, and then we got our numbers for all of these things. We added it up, divided, calculated this to get 0.25, and then multiplied across, and that's where we got the square root of 0.196. And then eventually we land on negative 7.901. Okay, so at this point, we have our t-value. So what I'm going to do is I'm going to erase the board, because we still have to determine whether or not we found significant differences between people, studying alone, working alone or working in mixed pairs. So what we have to do next is to run it through our system. So give me a moment, and I'm going to set that up. I'm going to take you through all the steps, and then we'll go back to the slideshow. Okay, so here we are. We're back at the board. So I erased all the calculations. I actually left the t-value there so you could see that that was there. And I'm going to work you through the interpretive process that we've been doing with all of our inferential statistics. So the first thing you're going to do is you're going to need to determine what your alpha was. And as you may recall, the standard alpha is 0.05, right? So that's clear. Now, is there any reason to believe that one group is going to differ from one another? Meaning, is there any reason before you do the research to suggest people working alone would do better than people who work in pairs? Probably not, and vice versa. So we're going to have our two-tailed test. We're going to put the two tails there. Now we need to do our degrees of freedom. Remember, each group had 8 participants, right? So 8 plus 8 is 16 minus 2 gives us 14 degrees of freedom. So at this point, I can go back in the back of my book where I have the table that says critical values of T. And then I'm going to go down to 14 degrees of freedom and then across to two-tailed test, 0.05, which gives me a critical value of plus or minus 2.145. So, okay. plus or minus 2.145. Now, the next thing I'm going to do would have been calculate my t-test, which I already did. I already showed you how to do that. But we calculated a t-value of 7.901. And now we have to make a decision. Are we going to accept or reject the null hypothesis? Well, this negative 0.7901 is more negative than our critical value of negative 2.145. So in this case, we're going to reject the null. And then we're going to interpret that as using an independent samples t-test, we found significant differences in productivity when working alone versus when working in pairs. Now, if your t-value is negative, that means the second mean was greater than the first mean. So we could actually interpret this, or we could go back to the averages. And we could say more specifically, we found that individuals who worked in mixed gender pairs performed significantly better than those people worked alone. That would be our interpretation. So that in a nutshell would be how you would calculate independent samples t-test. Now, I do have another test to talk about today. So let me reset up my slideshow and I'll be right with you. All right, so here we are. I want to finish our assumptions of the independent samples t-test, and then we can shift over to the dependent samples t-test. What are the assumptions that must be met in order to use an independent samples t-test? The first thing is that the groups have to be distinct. They have to be independent from one another, hence the name. So when you think of independence, I want you to think of, can you be in group 1 and group 2 at the same time? And obviously you can't, right? Either you're going to work alone or you're going to work in pairs, right? So based on this design, the groups were independent. We assume that there is a normal distribution. So it's interesting because that would assume that both of our samples have a bell-shaped curve, right? And then we assume that the variances of these two populations or groups are equal. Now, when you run an independent samples t-test in SPSS, we can actually test that assumption, right? There's something called the Levine's test, but if you fail to meet these criteria, then you run the risk of making false interpretations with your statistics, right? So these three assumptions should be met. All right. Now, what does it mean if we accept or retain the null hypothesis, right? Retaining the null does not mean we've shown it to be true. It just means that our test was not sensitive enough to detect significant differences, right? So we haven't proven anything if we accept or retain the null. Now, if we reject the null, that could mean one of two things. Either we have real differences between the groups, or we could have made a type 1 error. And I know I talked about a type 1 error in a different lecture. So we could have found significant differences between the groups, but in reality, it was due to some error variance, right? So we have to be very careful. Now, most researchers rely on replication studies. We don't assume that one test is sufficient to draw any meaningful conclusions, because any test that is one-off, you could find differences by chance, right? That's why we have an alpha of 0.05. We acknowledge that it's possible to find this occurrence by chance in up to 5% of the cases. Now, here is another example. Suppose we wanted to see if caffeine impacted performance on some kind of motor task. So we had a caffeine group and we had a placebo group. Now I'm going to set this up for a demo pretty quickly. And because I covered the formula before, I'm just going to use the numbers and plug the numbers in the formula, right? So give me a second and I'm going to set that up for us. Okay, so I just put the independent samples t-test on the board. So this is group 1's mean minus group 2's mean, right? Then we have n1 minus 1, which is the sample size for group 1 was 18 minus 1 times its variance, which is 4, plus n2 minus 1, which was 16 minus 1 times 5, divided by our degrees of freedom, times 1 over n1 plus 1 over n2. So now that I've done that, I could start working on the numbers. And let's see what we can get. So let me open my calculator. 19 minus 15 gives us 4, right? So our numerator is going to be 4 divided by the square root of 17 times 4 plus 15 times 5 divided by, let's do this, 18 plus 16 equals 34, minus 2 gives us 32, right? So 32 times 1/18 plus 1/16. Now, the next thing I'm going to do is I want to know what that is. So why don't we calculate that? So we do 1/18, right? Which is 0.05555, right? Plus 1/16, close parenthesis, equals, okay, got it. So together, this number is going to be 4 over the square root of, this number is 0.118, right? So I was kind of curious what that was. No problem. And now we do 17 times 4. 17 times 4 gives us 68 plus 15 times 5 gives us 75. This is all going to be divided by 32. So 75 plus 68 gives us 143. So let's continue our formula. And it's kind of getting squished. I'm sorry about that. So we have 143 divided by 32. And all of that is multiplied by 0.118. All right. So you see how I got that? I just added across right here. And then I'm going to continue my formula because I still need space. So here we are. We have 4 divided by the square root of 143 divided by 32. 4.469 times 0.118. Now, I'm going to keep this in my calculator, so I'm not going to round at all. So when we do that, we do what is 4.46875, which I put 4.469 times 0.118? We get 0.527. So now I have to do the square root of 0.527. Okay, so let's do that. 0.527, take the square root of that, and now we get 4 divided by 0.7259, 0.726. Okay, so now if we were to calculate the t-value, what we're looking at is 4 divided by 0.726, and what do we get? 5.5096, which is 510. That is our t-value. So now we know that we have to run it through that same process. So let me, just to save a little time, I'm not going to stop the video. So we calculated our t-value, no problem. All right. So the first thing we have is our alpha, 0.05. We have 2 tails. We have our degrees of freedom. Remember how we calculated that? So degrees of freedom for an independent samples t-test is N1 plus N2 minus 2. So that was 18 plus 16 minus 2, which is 32 degrees of freedom. Now we have to calculate our critical value. For calculating our critical value, we have to go to the back of the book. Now, here's a good example of something I said before, which was what happens if the degrees of freedom are not in the book. So 32 degrees of freedom and our critical values of T is not there. So to be conservative, we would actually move it to 30 degrees of freedom. So if I do 30 degrees of freedom with an alpha of 0.05 or a level of significance of 0.05 and a 2-tail test, the critical value to reject the null is 2.042. So 2.042. Now we already calculated our t-value. I left it there so I didn't have to use memory. So our t-value was 5.510. So now we have a decision to make. Right? So we have to look at whether our t-value is equal to or greater than our critical value. Again, if it's 2-tail, it's plus or minus. So once again, we're going to reject the null. We don't always reject the null. Sometimes we accept the null, but it just so happened in examples that we're rejecting the null. All right. So what does that mean? That means for an interpretation, that when we used an independent samples t-test, we found significant differences between the means. More specifically, people perform better on motor tasks when ingesting caffeine relative to the placebo group. So there were significant differences in performance when one used caffeine. All right, so I think that should do it as it relates to our independent samples t-test. But now we have to start talking about, I don't know if you noticed that the sample size was different, right? But there is a calculation. I want you to know it in concept. You don't need to know how to calculate the test, but there is a calculation for what's called harmonic means, right? So we can measure effect size using G. And if we don't have equal sample size, we could actually calculate a harmonic mean. And all that is you would multiply 2 times the sample size for 1 times the sample size for 2, divided by N1 plus N2, right? That's the formula. So let's see. I'm going to press pause on this example because I've demonstrated 2. I really want to get to dependent samples t-test or repeated measures t-test or match samples t-test. So when you're doing a match samples or repeated measures or dependent samples t-test, we're comparing a person relative to either themselves, one performance versus another, or we're comparing a person relative to someone they were matched against who is roughly equivalent on some other factors, right? So that would be what we do. So we're actually going to get different scores when we do this. So there's a whole different formula. And I'm going to say this now, but I think it's important to hold on to for later, is that when we calculate degrees of freedom, we're calculating degrees of freedom by pairs, right? Not total number of participants. Each pair is 1 unit. All right, so let's go with the example and then I'll set up the board, right? So the example given is that a researcher was interested in whether students who study while watching TV devote as much attention to their studies as people who don't watch TV. So they say, and this is a match samples t-test, the formula would be the same for repeated measures or whatnot, but 14 students are matched on school, grades, and IQ, and they were randomly assigned to each group. That's either a TV condition or a no TV condition, right? And then we were comparing whether these pairs did significantly from one another. So if you look at this, the first thing I want to do is I want to know how many pairs I have, right? So if I count rows, that'll tell me my pairs. Pair 1, pair 2, pair 3, pair 4, pair 5, pair 6, pair 7. Okay, so I have 7 pairs. Now there are 14 students. The easier way to calculate the number of pairs is take the number of students and divide by 2 because they were matched and put into a pair. So then we actually give them the test, and let's say we were giving an attention test and the scores range from 0 to 10. We could actually compare whether there were differences. So let me take you through these columns so we could work through it, right? Because when you calculate it by hand, you actually have to calculate the columns, right? So the first thing you're going to do is you're going to plug in your numbers. 6 for pair 1, 6, 10. And if the D stands for a different score. So what's 6 minus 10? Gives us -4. So that's our different score for pair 1. D squared is -4 squared, right? -4 times -4 gives us a +16. So 7 for pair 2, 7 minus 7 gives you a different score of 0. Squaring 0, you get 0. 6 minus 8 gives you -2. Square that, you get 4, and so forth. Eventually, what we want to do is we want to add up the whole column, right? So we want to calculate the sum of the D column, which is -10. And then we want to add up the sum of the D square column. Now, the reason for this is that we have a formula, right? And there are different ways to do this. Mean differences divided by, our standard error of the differences, right, score. So there are different calculations. So This is the most simplified explanation, but this breaks it out, right? So it says, okay, well, standard error of the differences, we gotta show the formula for that. And then our dependent sample or match pair sample t-test, we actually have to test it. So why don't I set up the board with the formula, and I'll plug in the numbers, and then we'll continue. Okay, so let's go through the formula, and I'm going to plug in the numbers. So if we were to go to the table, we said the sum of D was minus 10, right? So we're dividing that by N. Now, N here in a dependent samples t-test or a matched pairs is N refers to the number of pairs, right? So in this case, we had 7 pairs, right? 7 times the sum of D squared was 26, right? Minus the sum of the D column, which we said was negative 10. We're going to square that over N minus 1, which was 7 minus 1. Okay. So now we can get out our calculator and start working through. So we know that it's minus 10 divided by 7 times 26 gives us 182 minus negative 10 squared. That's easy. I won't even put that in the calculator. 10 times 10 is 100. 7 minus 1 is 6. All right. So now I'm going to bring this up to continue my work. So we have minus 10 divided by the square root of 82 divided by 6. So what is 82 divided by 6? We get minus 10 over the square root of 13.667. Okay, so let's take that. We do minus 10 divided by the square root of 13.667, and we get a denominator of 3.697. And now we just have to do negative 10 divided by 3.697, which gives us a negative 2.705. So that's our T. All right. So now we've calculated our T. Okay. So now we have to plug all this in and interpret it, right? So I'm going to keep the T up, but I'm going to take it through the interpretive process we've been doing for a while now, right? So I'm going to plug in the alpha, again, 0.05. The number of tails is 2 tails. The degrees of freedom. Degrees of freedom is number of pairs minus 1, or 7 minus 1, or 6. And then we get our critical value. The critical value, now I'm going to have to go back to the back of my book. And for 6 degrees of freedom, with, you know what, I want to show you what would happen if we changed this to 0.05 to 0.01. So now we're being more stringent with our alpha. So instead of having the standard 5% error, we want to do 0.01. And I actually did that for another reason, which I'll explain in a minute. So if I go down to 6 degrees of freedom, 2-tailed test, go across the 0.01, I get a critical value of plus or minus 3.707. Okay, sorry about that, 707. Now, my t-value was negative 2.705. Now, the second reason, and I'm going to be completely transparent about this, the second reason why I picked 0.01 is I got tired of rejecting the null. I actually wanted to show you what would happen when we compare it and the t-value is not equal to or greater than a critical value. So our decision here would actually be to accept the null, which would mean if we were using a alpha of 0.01, we found no significant differences between those people who watched with the television on versus studying with no distraction. That's what that would mean if we accept the null, right? Well, why did I put 5, 7? Interpret. So in this case, we're going to accept the null because of the alpha. Now let me show you something cool. What if we did the same thing and I kept my original 0.05 alpha, 2 tail, 6 df, right? Well, the critical value, because I'm allowing more error, would be quite different. So the critical value at 0.05 would be plus or minus 2.447. Let me just double check that to make sure I got that right. Yes. All right. And then if we were to take that t-value of minus 2.705, our decision here would be to reject the null. Now, I love this demo because if we compare the two, if we look at the critical value, when we have a stringent alpha, when we're not allowing as much error in our interpretation, the critical value is higher, which means it's harder to reject the null. When we have the standard alpha of 0.05, we're allowing more error, which means the critical value is lower. And sure enough, in this scenario, it changes our decision, right? So our interpretation in this case would be to say that studying with television on, actually people perform poorer than people who studied with no TV on. But I love that because you can show the power of your alpha, how it affects your critical value, and how it could affect your interpretation. I think hopefully that was something cool. Hopefully you liked it. For me, I was just trying to show you something beyond what the book talks about. So let me go back into our slideshow. If I could, I have to open the slides up. I guess I shut them. So, all right. So what I find cool about that process is that you can see that the mathematics shift depending on how much error you're allowing. So that affects your critical value, and sometimes it affects your decision making. Now, I said to you, I probably said this a couple lectures ago, but the idea of our alpha, our standard alpha in science is 0.05. If we're doing an exploratory study, it might be 0.10 or 0.20. That's called a lenient alpha. If we're doing drug studies, we might do something which is a more stringent alpha of 0.01 or 0.001. And your book has all of these in the back for the table, so you could figure it out. All right, so now let's compare the t-test for match pairs versus t-test for independent samples. The reality is the numerator stays the same, whether it's an independent samples t-test or whether it's a match pairs t-test, the numerator is still taking the difference between scores 1 versus 2, whether it be the sum of the scores or the mean scores, right? Mean 1 minus mean 2 in independent samples, and in match pairs, it's person 1 versus person 2. Now, the denominator actually gets shorter or smaller, and we see that the critical value gets larger for match pairs t-test. Now, there are other scenarios for repeated measures. It's the same thing as match pairs, but repeated measures is when you're going to give the same people over and over. If you do that, you might need counterbalancing, and you have to worry about carryover effects or order effects. So, but we could talk more about that. The next video is going to be about the one-way ANOVA. So let's stop here and we'll continue. All right. I'll talk about the ANOVA next time, and then I'll also talk about chi-square. So to be continued.